material for exam one. Yes, a couple of other things that go along with it. Exam one is October 1st. It's hopefully over the course of the weekend, I will have that review recording done. I'll send the same one to everybody. It's just me narrating. I take the exam and start talking from it. All these classes are, save the one I teach on Wednesday afternoon and I do a week in a day, and there's only about 13. All these other classes are jammed. So I had to, yeah, it's the same exam. There's 3 different colors. So all I've done is flip-flop the questions in different orders. So because and don't misunderstand me, as my mom used to say. I'm not accusing anybody or saying anything like that. But you can't help it when you're sitting next to people like that. You just can't. We're not static like things like that. Okay, and that'll be the day that they bring some dignitary to show them what's going on in our classes, and it looks bad. So it's all saying about impropriety. Not only is it impropriety, but the appearance of impropriety that are there. So I'm not casting aspersions. This is just it's a preventative measure. So I want to give everybody to acquaint everybody. It's just when you have a crowded classroom, you got to do this stuff. So here we go. Let's begin. So and hopefully you did receive this. I had sent this PowerPoint earlier because I can't fit them on Blackboard. This the one that's this 3A that's there. That's that. And so I just sent 3B today. I use them because, and not the animations on this one aren't particularly good, but I use them because I think it's valuable for you to be able to see the animations when they're really good. And explains what I think is relevant, and particularly for the first thing. So are you able to follow these now if somebody's looking at it? Because one of the students in the class one of the students said he didn't get it. I resent it. If there's a problem, email me and let me get in touch. Nevertheless, basically this is all about leading up to what's in the membrane and how things move across the membranes, which will just start today. And that, because that's on the next exam. But effectively, the membrane is made of phospholipids. It's in a bilayer. Naturally, you put phospholipids in water, they're going to form a bilayer. And the terms that are important are hydrophilic and hydrophobic, because those are the terms you see on the exam. We use the scientific term a lot of the times that are there. The hydrophobic, the ones that don't like or hate water, or afraid of water, that's actually what a phobia is, effectively, what it means, they come to the middle and naturally form this bilayer, even though it is not effectively bonded together or anything like that. There are also, and then the beauty of it is protruding, whether it's a cell membrane or any other membrane, the water-soluble pieces protrude inside to create change and are compatible with the interior of the cell, let's say, and the outside, so it's a water-soluble environment on both sides. So it's the elegance of being able to communicate, sometimes directly and sometimes indirectly. The glycolipids, they're just nothing really special about them. We're going to get to the whole idea of the surrounding nature of sugars. They're everywhere. The fancy name is glycocalyx or sugar shell, and it's so terribly important because it provides attachment, it provides identity, it provides a way of tethering cells together. You got to have something to attach to, and basically those sugars are a useful framework, so to speak. And cholesterol itself, which plays an important role. The amounts are not really that critical for us at this point in time. To know that it's mostly phospholipids, maybe like say roughly 80-20, phospholipids and cholesterol is about all you have to remember, I think. And cholesterol is about the stability. The heads, the tails, all that nonsense. It's the proteins. All that time I spent folding the stupid papers and doing that, it's all about to make you understand the important role of those proteins and the fact that they can literally stick themselves in a membrane. They can be tethered there or they can move around freely, because when proteins and polypeptides have so many of those different amino acids and they inherently fold because of those globules, can insert themselves in the membrane fairly easily, and they can also move around. They provide a lot of the mass, as you can see, and they account for the functions. The fancy terms, integral and peripheral, are not a big deal. The integral just means they're in the membrane, and inevitably, if it's stuck in the membrane, the peripheral part means what's protruding out or protruding. Most of the proteins that we look at are a combination of integral and peripheral. I think that's just making it a little too, it's making something that shouldn't be as complex. So integral, firmly inserted, they span the membrane. And again, because of the way they fold, hydrophobic in the middle, and hydrophilic outside, and they have a whole lot of functions you're going to see shortly. Peripheral proteins, outside. I don't know if they're that loosely attached, but we'll go with it for the time being. I'm not going to ask you about it. And they have other, we'll have more about what they do as opposed to the structural stuff that's there. We're not doing molecular biology. My colleague just gave an exam. She teaches that in the spring. And this is a terrible illustration, but thankfully they blow up each one of those. And these are the 6 roles. I didn't tell you, I like your class better than the other class. There's a matching. It's going to be, and this is part of it. It's going to be kind of like cell to cell, transport, identity, that type of stuff. And I'll give you what in some way, shape, or form. And I'll even tell you about it when I do the review. And it'll be, so basically you'll have 5 or 6 of these, and you'll have to identify which it is from my description of what's going on. Is it a cell-to-cell recognition? Is it enzymatic? Blah, 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 blah. Fair game. I'm telling you what's on the test. I'm happy to do that without telling you ahead of time the answers to the questions, other than, one of them's, things that are obvious. Sorry. It's bad. You're improving. God bless. Until heaven. I mean, you guys are all in school in COVID like that. If somebody coughs once, everybody in the world went freaking nuts. Like we don't cough or sneeze. Bless you. I digress. All right, transport, moving across the membrane. Okay, there's a couple of ways we look at it. We're going to look at diffusion and simple diffusion. That's, a lot of things that are membrane compatible, meaning small, non-polar, or fat soluble. That's a whole different ball game. But when we're looking at these things that are water soluble, water itself, or small charged particles, or even sugars and other chemicals that can move in and out, that can get through based on their size, that's where we look at these transport proteins. So some of them function as, we'll talk about them as channels, and some have the ability to change shape. Some, in order to change that shape or to facilitate or enable that movement, they have to utilize energy. We are not going to get to that today. We're going to get to that on Monday. Whenever we call that active transport, when you have to add an ATP to move something. Another name that you'll see, and the most famous one, is a pump. Pump and active transport are synonymous. They both mean we have to add energy to make that system work. We are going to talk about them down the road. They're called sodium potassium pumps. They're the ones that are the most studied by far. So here you have a channel protein. You're going to get tired of hearing about channel proteins because some of them, what allows some of them, things automatically get through. Sometimes chemicals enable them to get things through. Sometimes changes in voltage, electrical charge. You're going to hear about voltage gated and leakage channels and ligand gated channels, all these types of things. You get sick and tired of it, but that's part of why I'm just trying to present it to you. So when we have one that's always open, typically it's for something like water or a very small molecule like sodium and potassium. As a charged particle. Again, by definition, those are hydrophilic. They're either water or compatible with water. That are there. These animations are not so good. Receptors are probably the most important in the sense of how we can induce the cells to do a variety of things and not having something enter. Most of it, if it's a protein or a very large molecule, it can't get into the cell. It can't get through the membrane. So in order for it to have to do that, okay, it basically conducts the message from you have something. Somebody knocks on the door and you're inside. You're going to get up, you're going to open the door. They're still outside. So, you know. But signal transduction is just that. You get a big molecule, it could be insulin, which is an enormous protein, or even a good sized chemical that can't get through the membrane. It's not lipid compatible. It's water soluble, but it's too big without disrupting the membrane. It attaches here. So it's like something grabbed my hands on the outside, my body is in the membrane. And then all of a sudden, by the interior, causes me to kick or do something like that. So from the outside, it's exerting an impact on the inside. In this case, somewhat indirectly as it goes through this protein. And what happens, particularly with insulin, which is the best example that you learn about in AP2, it sets off a chain reaction. Insulin doesn't just open the door and say, come on in, glucose. Insulin causes the cell to replicate. Insulin causes the cell to utilize sugars as an energy source. And there's a whole, it's almost like a little mini chain reaction on the inside by things going along the interior of that membrane. It's got a fancy name of the enzyme that's involved called tyrosine kinase. You do not have to know, and you probably, for me, you wouldn't have to know it if I was doing AP2. But, you know, it's a well-known passageway. So it's changing things without entering the cell. So to me, that's an indirect method. Enzymes. Think digestive. Okay. We spent so much time talking about lactose and sucrose. Effectively in your gut. And you'll see an example. It's a thing called a brush border. Maybe you looked at it in lab with some projections or under a microscope. In the small intestine, where most of the digestion and absorption occurs, we absorb. This is the whole idea of lactose intolerance. Only simple sugars. We only absorb amino acids. By and large, by the time it gets to the close to the small intestine, to the cells in the lining, okay, all of those cells are like little fingers that project. We call them microvilli, little fingers. And there's tiny columnar cells all over them. And the border, the edge of those columnar cells have proteins that act as enzymes. That's where the lactase breaks lactose into glucose and galactose. That's where table sugar becomes glucose and fructose. And that's where it gets absorbed. So we call them brush border enzymes. The classic example is in the gut. Everything, again, is about shape and surface area. So those little fingers that are everywhere, it's an extraordinarily unique area with regard to making a massive amount of surface area in a very small place. Because that's what your gut's all about. That's why in surgery, when somebody has a tumor, when somebody has a terrible ulcer, we can cut pieces of it out and you're still able to survive. Okay, up to a certain point, obviously. There's a lot. We have a lot of built-in redundancy, thankfully, in our body. So, I mean, it's the old story. You could exist with not just one kidney, with 1/4 of one kidney working. That's why you can donate a kidney if you're so inclined. Probably now we get to really the intricacies of this glycocalyx or sugar shell. These are called, effectively, it's proteins with sugars together, but so collectively we call these so-called glycoproteins. And the sugars, other stuff can attach to them. Perhaps the single most important thing they do that starts right away in our lives is cell-to-cell recognition. These short chains of carbohydrates, glucoses and fructoses basically, vary a lot in individuals, dramatically so. There's some similarities, of course. It is the basis of the ABO blood typing system. So nothing more than variations in these, except because of those variations, as you learn about when you study the blood in AP2, it can be devastating. I mean, it can rapidly be fatal if you're type A APOS, and you would get a transplant of something with BPOS, or you get a transfusion with that. I mean, you could die right away. Shortly thereafter, kidneys can shut down. Massive, massive damage. I know from what I speak, I've had, unfortunately, a lot of units of other people's blood. Thankfully, I have A positive. It's very easy to match up, comparatively speaking. So what does it mean by the cell-to-cell recognition? When you are born, your immune system is not really that functional. It takes about 6 months. For those first 6 months, you're relying on your mom's chemicals. You're relying on your mom's antibodies, your mom's immunological products. In the meantime, as your immune system ramps up, there's a process called self-non-self identification. White blood cells are being produced, okay, all over. And they don't have vision. They're not special in that regard. All they are, they're just we call it rolling. They're rolling through your system. They're rolling over tissues. And at that point, they're recognizing these little chains of carbohydrates. And if it's in the first 6 months, they go, aha, self. And after that, or if there's something in the mom's white blood cells that says, wait a minute, that's a virus, that's a bacteria, that shouldn't be there, the mom's white blood cells and related chemicals will take care of it. After that sort of 6 month golden period, it's not a hard date or anything like that. Once the immune system gains competency, it continues, those white cells continue to roll over everything. So if they have a marker if the marker is supposed to be like this and all of a sudden they get one that's like that, they latch onto it. And that starts a chain reaction of chemicals that basically is an immunological response with inflammation, more white blood cells. Effectively, it's an invader. That's why this is so terribly important. All of our cells have markers. But when someone is compatible with a transplant with somebody else, enough of those markers are similar that we can control the immunological response and they can survive. Unless it's an identical twin or it's tissue from yourself, there's always going to be a response. When I did skin grafts, the only ones I did were auto self grafts. I take a piece of skin from one place and put it on someplace else. Most skin grafts are like that. So you don't have to worry about an immunological response. So that's the next part. Now we take more of that. So we're not only limited to sugars, we have fibers. This is the whole idea, okay, of cells communicating. When you have epithelial cells, lining cells, they're sheets. They cover a surface like that. It's not like a little line, because when we draw them, we see a line of cells. The reality is a sheet of cells. So what do they do inside of a blood vessel? They allow red blood cells and other entities to move smoothly, effortlessly. Because if they start to clang together, it makes things clot. So it's a line, but it's not linear, it's three-dimensional. Think of it as a sheet. When you have connective tissues, the cells are not tethered together like the lining, they're apart. So they pull and tug on one another. But first they have to attach. All those fibers utilize that for attachment. The pulling and tugging sometimes is used to send signals. If it's being excessively pulled, maybe we have to have, let's say it's a fiber site, come back. Remember the terms from lab, become a fibroblast to make more fibers, to strengthen it. So this is all terminology you should have happened in lab. Okay. So part of that, all this tethering process is part of it. So these attachment is there. Cells anchor to membrane proteins, maintains the cell shape, fixes the location of certain proteins, plays a role in movement when they move over each other. So cell to cell, we see it. When you begin to see the relationships of as they begin to pull apart or move apart and things like that. So that's an important role as well. And here, this is the one we spend quite a bit on. These are called CAMs, the acronym for cell adhesion molecules. Basically how cells hook together. With the exception of effectively red and white blood cells. In this PowerPoint, they talk about sperm cells. To me, sperm's not really a cell so much as just a carrying vehicle for a 50% load of genetic material, if you want to get technical about it. But from a cellular perspective, white cells are probably the best example. They function as an aggregate, as like an army of cells. All other cells are joined together in some way, shape, or form. Some right next to each other, like lining cells, some far apart, depending on the type of connective tissue that you already studied. And so we look at these adhesion molecules. So again, to review, there are 6 of these things that are there. So you get the joining, the attachment, recognition, enzymes, receptors, transport. I mean, those are basically the categories that are going to be the subject, sort of the answer key for all those matching things. You don't have to thank me. It won't be. It's still going to be hard. So here's the sugar shell, glycocalyx, and it isn't just necessarily proteins. It can be other fats. It can be other things. They don't have to be it. There's no consistency to it. There's a variety of things that we can attach to facilitate those shells being in contact with one another. So, and this is really the cell-to-cell recognition and the self to non-self is vitally important. This is the interesting, another clinical nugget. And it's why, I understand, this is why, now they're showing the example of cancer, why we have to address things early. Because as these cancer cells begin to become enlarge and grow and spread, by definition, it's an aberrant cell. It's changing constantly. Our white blood cells, we call killer T cells, known as cytotoxic T cells, that attack cancers for us. Basically, they are about those recognition proteins. The proteins are changing. Those sugars are being altered. It can't recognize the cell. So the faster that you can get to it, the better chance you're going to have of destroying that cell. I mean, that's why sometimes when things get too far gone, there's not a whole lot you can do. That's a sad reality for people who are in clinical fields. Sometimes, no matter what your best efforts are, you can't win. Someone's not going to survive. So then it's what we call palliative treatment, just trying to make them more comfortable and being able to survive and enjoy a certain quality of life, for the most part. And we see this in so many different ways. That sort of manifests itself when you have an infection in somebody, particularly those at risk. For you and I, assuming we're all relatively healthy, getting a regular virus like a common cold or a strep throat kind of stuff we'll get over. When you get somebody who's impaired, like a diabetic or someone with some other underlying disease, you got to treat them right away because their ability to deal with that is very, very limited. That's sort of what I can tell you about that. The part of the junctions is important. Okay. And again, they use that sperm cell. I don't necessarily buy it. Okay. 3 different types. Tight junctions. Tight junctions, they're all of these are made of proteins with varying kinds of fibers, sometimes associated with it, sometimes not, or other basically structural material. Tight junctions mean one thing, watertight. Desmosomes, the strongest. They hold on the best. They tether cells together so they can't come apart. Okay, they have a certain amount of give built into them, but it's very interesting. They use the term, they have a zipper-like arrangement that you'll see from the illustration. And gap junctions. Gap junctions are the way cells can communicate. Sometimes you can tug on a cell, but most of the time the cells are going to either get electrical signals or chemical signals between each other. That's where the gap junctions come in. You'll see these latter 2 very significant in the cardiovascular system because that's how your heart beats. You'll see that shortly. So tight junctions. Imagine you have a belt here and a belt here and a belt here. The more of these belts you have, and your neighboring cell, an epithelial or a lining cell, has the same belts. So not only are you have a series of belts, proteins surround, they're tethered to the adjacent cell. And what that is, it basically creates very, very close contact between you. The more of those you have, the less likely it is things can get in between the cells. If you have 2 cells together, there's a little gap space. I mean, water can get through that. Little sodiums and potassiums can get through that. But the more of these junctions we have, the more likely it's going, and that's why I say the term watertight. Where is that applicable? In your brain, for instance, the capillaries in your brain have so many tight junctions that they are water impermeable, to the point where if we want to get medicine into the brain, we have to use things that are chemically designed to be fat compatible. So every medicine doesn't work to get into the brain. We call it the blood-brain barrier. It's very, very famous. That's there. In your stomach, okay, the stomach is filled with hydrochloric acid. Nasty. Okay, we have a certain layer of bicarbonate-laden mucus that helps to neutralize it. But what really prevents it from damaging the interior of your stomach are tight junctions on these lining cells. The lining cells are subject to so much chemical action, and plus the food and irritation and mechanical processes. Every 3 to 6 days, they are all replaced. They're continuously being replaced. Gastrointestinal tract has the most active mitotic area. That's why, unfortunately, we get so many problems associated with it that are there. However, okay, the tight junctions prevent that acidity from coming in and causing something like a gastric ulcer. An ulcer is like if somebody went in there and scooped out sharply, gouged out a piece of the tissue, and it starts to bleed, and it's extraordinarily painful, and people can die from them, they can bleed out from them. Okay, what creates that ulcer? Somebody drinks excessively, somebody, basically overindulgence in caffeine, various kinds of chemicals. There's lots of things that can make that stress. Most famously, non-steroidal anti-inflammatory drugs. They're popping a leave and ibuprofen like they're candy. So there's a lot of different things that can do it. You look about that in GI, but that's where these tight junctions are really important. So they're like this. Imagine a series of these interlocking proteins, and effectively, it's like you have papers that are together like this. And effectively, what we would do is you put one staple, you'd hand in a report, hard copy in the old days. Well, it's fine, stay together. Oh, you make it a little prettier when you turned it in. 1, 2, 3 staples. Now I could open and read it like a book. Water could still get through there. Anything could. So if you put a series of those staples, you basically limit the ability of things to get in between the staples that are there. You'll see that in other areas. Even in your gut, okay, there are areas farther down that are designed for that passage. They're designed for things to go through. In your kidney, they're designed for things to get through in between the cells. It's got a fancy name that you'll learn about called transcytosis. I didn't make it up. Strong ones, desmosomes, rivets. It's like rivet would be like if you see a skyscraper go up and all that giant steel frame, and you have the working men and women up there, with riveting guns trying to make those connections so they can't possibly move. That's the idea, and that mimics what we do in our body. So it has linker proteins that act like a zipper, so there's a certain amount of give. The best example is your heart. When you study cardiac muscle, you're going to learn about an area where the cells join. Basically, here's what happens in the heart. When one cell fires, it immediately tells the next 2 cells in line, your turn, you fire. And those 2 cells tell the next 4 cells in line, you fire. And they do that all continuously from where they start, call your pacemaker, and in less than a quarter of a second, they all fire at once and then they relax, roughly for about the better part of 3/4 of a second. And they do that more rapidly than once a second, every second of your lifetime. Okay, so it's constantly moving. I mean, if you didn't have a certain amount of give, you had to have a ton of strength, that's a desmosome, and a certain amount of give, you would start tearing them apart. That's the beauty of that. How do they pass the signal? Now it's your turn, almost instantaneously? Gap junctions. And another name you'll see for the gap junction when we get there, called nexons. And they have both those names. And they are ways that whether it's chemicals, whether it's electrical signals, whether it's charged particles, are be able to tell one cell to the next, to the next, to the next. So there's the gap, I'm sorry. So linker proteins, plaques, keratin, strong structural protein, a certain amount of give. Here you can see this is what they mean by those ones that have the give associated with it. Fibers attaching one to the other into the inside of the cell. You'll learn what intermediate filaments are when the time comes. And not too long from now, we'll get to intermediate filaments and microfilaments and microtubules, all the things. Here's the transmembrane proteins, connexons or gap junctions. They're little openings. You already saw the biggest version of those, the nuclear pore, when we talked about DNA and RNA. DNA is too big, RNA can get through. But most of the time, they're a molecular size. Calcium, potassium, chemical signals, okay? Simple sugars, tiny molecules. So cardiac and smooth muscles certainly are the best example of these. So you see these in different places. So this is just setting the frame for all of this. So that's what they look like. You can see them a little bit. They have all three here. And most cells have, to a certain extent, they have combinations of those. Here you can see they're arranged as each a protein embedded in the membrane with an opening, whatever the size of the opening, whatever it's compatible with. Again, they're not generic. Well, anything can go through that membrane as long as the hole's big enough. No, they're specialized. So effectively, that's what it's about. Substances constantly moving across plasma membranes that are there. And so really what happened, just to finish this piece, once this concludes the material for exam 1. Bang, here, done. Everything else now, which and really the start of what we start looking at in the next slide is called movement across membrane. Everything has laid the framework for understanding this whole idea of selective permeability and why it is so important. So it's constant. Okay. Understand that living systems are constantly in motion. The only way things would stop moving in our body, unfortunately, is if we were deceased. The only way things stop moving in any living system that would be effectively at absolute zero. Even as we chill things, molecules still move to a certain extent. Our bodies live in a state of what's called equilibrium. Basically, there's movement in and there's movement out and different controlling factors. When something is in equilibrium, basically it means there's zero net movement. As many particles are moving in as are moving out. Or we have other mechanisms for that. So that's what you experience equilibrium. Okay, if you have something that's warm and you put it in ice and you put it into a glass with some ice, sooner or later it's going to chill roughly to the temperature of the two combination. It'll stay there as long as, and the ice, as you can imagine, eventually is going to start melting. But effectively, if you're waiting a little bit, it'll have a moment to, we call it equilibrate. So it'll get closer to that end point between the temperature of the liquid and the temperature of the ice when they come together. Biologically, equilibrium means particles are moving inside and outside, but there's no real net movement that's there. Not all systems have it. Some stuff is always moving in, some stuff is always moving out, and we're compensating for it otherwise. So it's all about selective permeability. We either use ways that expend energy, and we're very, very frugal with energy. So anything that expends energy is called active transport. Again, if you see the word pump, it means active transport. When we start looking at mass movement of materials, endocytosis and exocytosis, those all require energy. Those are all different forms of active transport, although we have a different name for it. But the one that we do the most, because it's the most energy efficient, is passive transport. Indeed, we'll spend energy to make it easier for things to move passively. We accomplish this through 3 different means. So we look at the passive transport first. We're just going to touch on it today. We start with simple diffusion. What makes it simple, okay, is it doesn't normally require any specific modifications in the cell. Typically, this is for either small lipid-soluble materials or nonpolar covalent. So tiny things like cholesterol, which even though it looks big with those 4 chains molecularly, it's not, with those 4 rings, so to speak. That can move across the membrane. So things like that, of that size, can easily, if they're fats, move in and out. They're lipid-soluble. They're lipids themselves. Okay, oxygen, carbon dioxide, they can move across easily. They are small nonpolar covalent. That's when we talk about simple diffusion. Water is different because it has a passageway, and we address water differently. And this is where we're going to start to get into some definitions. Talking about diffusion, and we're talking about facilitated. Facilitated diffusion means things are moving, but to facilitate or enable it, we have to have a passageway, and in some way, shape, or form, allow it to open or allow it to close. So we're facilitating or enabling. These are the terms we use on exams. Solutes, it basically means stuff, dissolved in water. So when we're talking about facilitated diffusion, basically we're talking about solutes and their relationship to solvents. In our case, it's water. So you have to get used to that terminology. When we get to osmosis, it's the movement of water. Okay? So it's a very, very specific kind of relationship. And I use the terminology because you're going to end up seeing that terminology, not only in my exam, but probably in exams you're going to take in the future. So it's better to use it now in case it rears its ugly head to get used to it. So we always look at the relationship between stuff dissolved in the water, solutes, and it's a generic term. It could be sodium, potassium, chloride, glucose, whatever, and water itself, which is the universal solvent in living systems. So diffusion, natural movement of molecules from higher concentration to lower concentration. So that's the framework. What drives the bus about molecules moving passively without having to impart energy is concentration gradient. That's the big play. Does temperature play a role? Yeah, they move faster, they collide. Does size play a role? Yes, smaller moves faster. But the big deal, you're in the room here. If somebody comes in this room, where can they sit? I mean, we're pretty darn full today, and thank you. I do appreciate that. We've got a few little seats over here. Back in the old days when you went to the movies, before you had the assigned seats, those nice reclining chairs, love those. Okay, spoil you. That's why you hear old people snoring in those. They got to sit over here, right? What is the idea that what concentration gradient does? The molecules are close to each other. They collide, and they go to the area where they're less likely to collide. They get pushed away. Just if you were in a crowded room, maybe you like to stand next with shoulder to shoulder. You're probably going to look for some space someplace. So it's nothing unusual. When we go against that, we have to expend energy. And so if you have that, when everybody's getting out of the movies, okay, and everybody's falling out because the credits are running, everybody wants to get to the bathroom. If you're all walking back in, you start to walk out, and all of a sudden, I left my sweater. Okay, you're trying to push back in against the crowd. It's not easy. Everybody, what the heck, you're pushing away from it. You're expending energy to get there. There's a zillion analogies. When you're going with the crowd, it's easy. If you're at the football game at halftime, everybody's going to get off to go to the bathroom, go to a food stand or wherever they're going. Just stand up. Let the crowd carry you. It's not very energetic. Everybody's pushing in the same direction. That's the idea behind it. And whatever analogy works for you, I don't care. All molecules have random high-speed movement, intrinsic kinetic energy. They're molecules. They don't stay stationary. They collide, scatter to lower concentration areas. You'll drop the blob of ink or the piece of dye in the beaker and watch it fill up. Interesting note that the students found interesting in the previous class. You hear about people get very excited about amounts of blood and water. A thimbleful of blood will make a gallon of water turn red. It's a whole lot of hemoglobin molecules. So sometimes certain things change color. When we see a bloody urine, that's a very ominous, unless somebody was at a football game and got struck there, and okay, maybe there's some blood coming from some damage to the kidney. It's probably going to be transient. When somebody's peeing red, that's not a good sign. The most common reason is bladder cancer. Most time when we talk about hematuria, it's usually microscopic in nature. So those are the factors that are there. Equilibrium is reached only when there is no net movement of molecules in one direction only. So the stuff that's had to move in moves in. The stuff that's had to move out moves out. At that point, we get subtle changes. I'll want to move out, want to move back in. That's the idea of equilibrium, and it's continuous in both directions. So a natural drive, nonpolar, hydrophobic, lipid core plasma membranes create concentration gradient barriers, blah, 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 blah. Not everything can move. Again, oxygen and carbon dioxide, for the most part, freely. Water, there's little pores, freely. Other stuff requires special passageways or special arrangements. Okay, so simple diffusion, and the classic example you see of simple diffusion is in your lung. That's a lung. Okay, you have lung here, a ton of oxygen. Capillaries, small blood vessels, they both have the same lining. They each have simple squamous lining, which is basically just a giant amount of membrane, the nucleus. So it's all about being able to move this fatty membrane. Okay, and they share a base layer called basal layer. So it's a beautiful design. So here you have an abundance of carbon dioxide. What happens is, and that's the beauty of simple diffusion, the fact that oxygen is moving this way, a lot of oxygen get out of the way. It doesn't include carbon dioxide from moving in the other direction. So anything, and not just two, you have 6 things, 10 things moving simultaneously. That's the beauty of simple diffusion. As long as the particles are there, it's not going to distort the membrane. They're basically the membrane. They're so similar to the membrane, they can almost walk through it. I'll walk you through it. That type of stuff. That is simple diffusion. The classic example, surely, is the distinction. And if you went down to the tissue level, you would see the same thing at the tissues when it leaves the capillaries and enters the cell. It's very, very similar to that. Okay. That's really an important point. We'll find down the road when we have facilitated diffusion, now we have to do something to allow these non-lipid soluble and polar molecules to get through. Okay, they need a carrier molecule. Some of them are there. Now, the question is, the variations between them, how they operate, you will see. The classic example of true facilitated diffusion is the role that insulin plays, albeit indirectly. Insulin isn't attaching to that outside and magically opening the door for glucose to come in. It's that chain reaction. It's one of the many things it does. Okay, but effectively, insulin is the facilitator, the enabler of glucose entering the cell. Whether it does it by directly causing that passageway to open or through some chain reaction of other events. So, I mean, there's a lot of specifics. So I want you, and there's a lot of examples of facilitated diffusion. And osmosis, which always confuses the student because you're always thinking in terms of the particles, you have to understand the relationship to water. Because water is nothing more than another particle. And so we have to we're looking at the actual concentration of water. It's there. So that's part of it. Now, here's the clinical example and a little comment in the last couple of minutes. Severely damaged. Okay. The biggest example of that is, I know you did burns when you're talking about skin. The biggest problem with burns, the immediate problem is this with bad burns, is the loss of fluid and electrolytes. It could be so severe as to be immediately life-threatening. The second biggest problem is afterwards is burnt skin and burnt tissue are comfort food for bacteria. You have to assume they're going to get infected. You have to treat them with the idea that they're going to get infected. We have to debride or remove all that dead skin that's there. But the first thing is electrolytes. So I told everybody the first time I worked ER on relief, no, the second time I worked ER. We were my first wife was head nurse of the ER, or assistant head nurse. She was in charge of the ER. Christmas night. Being Jewish, we worked Christmas so our friends could, be with their families on important holidays. Nothing unusual about that. We had a disaster occur. There was nothing going on. Silence. We had an occasional person come in for the first 4 hours. About 6 o'clock, these days there wasn't electronic. A red phone rang. A flop house where homeless men for 50 cents. It's 48 years ago. Homeless men, about 100, paid 50 cents for a bed to sleep. It was ridiculously freezing Christmas night. We ended up, there was probably 100 or more of these men, maybe 150. They moved them to all the city hospitals. We were in North Philly. We were probably a mile away from Temple University Hospital. Two big hospitals. We were one of them. We had about 200 beds. I think we got 50 because we were 2 blocks away. We got 50. 2 died in ER. 2 died up in ICU. Everybody else we managed to survive. I just was learning how to start IVs. The guy who was the attending was also a part-time. So he was a urology resident. He goes, as soon as they come in, I want 2 wide bore IVs in every one of these patients who comes in for fluid loss. Okay, and we got to give them medication. I'm like, well, I've got to just do it. And after the first few, I got real good at that. One here, big. It was not little butterflies, big time starting IVs. At the same time, I also learned to do arterial blood gases because we didn't have that neat little pulse ox thing that didn't exist. If you want to know what their gases are, you had to do an arterial stick. So when you're under, and any doctor, any nurse you talk to, believe me, they'll give you war stories that will be just amazing. It's not anything unique to me. I have some fun ones, we all do. But that's how I learned to do that. And we're debriding dead skin, peeling it off of people, hitting them with heavy doses of morphine and other, because the pain is intense. And you're thankful to survive. I saw the Red Cross did a very good job that night. I mean, I can't imagine how they could find clothing that we had to peel off people to replace it in a matter of an hour or two. So it was really a remarkable evening, well said. Nevertheless, more war stories for you at a future time. Thank you very much. Have a wonderful weekend. We will address the rest of passive movement and begin active transport on Monday.